Anyone who's, has some inclination, not even like any interests, say, oh, what is that about? What is graduate school about? Why do I want to spend another, 4 to 5 years in school when I can, go get a job and stuff like that? And what that's about. There's this program called CalBridge. They bumped the amount of scholarship money up to $15,000 per year now. And it's available for physics, astronomy, computer science, engineering, mathematics, and statistics majors. And the application deadline is basically about a month from now. And you might think, oh, I'm going to spend that weekend, type it up and stuff like that. The application does take a little work. You need to get like a couple of recommendation letters. And you also want to apply focusing on what CalBridge is looking for. So if you're interested in applying, really talk to me or the liaisons in your department. So if you're in CS, I think Melanie Martin is the person to talk to. I think in math it's Jung Ha. But either way, just talk to me if you're interested, and I can guide you through the application process. That way, we get you on your way. And one more thing to note, it is a program that's designed for 2 years of your the last 2 years of your undergrad. So this class is kind of like the ideal recruiting pool because most of you guys are either sophomores and juniors, right? Where you basically have maybe a year and a half or 2 years to finish. Okay, that's who this scholarship is targeting. So talk to me as soon as you can if you are interested, have some inclinations like, oh, after I graduate from Stan State, what is this grad school thing about, okay? And why would I want to go to school longer, okay? Okay, and it's actually not really school, okay? Okay, so today we are starting chapter 28, which is the last chapter we're going to cover before midterm number 2. Midterm number 2 is on the 26th or 27th. It's the end of March. It's 2 weeks from now, 2 Mondays from now, okay? And that's going to cover chapter 25, 26, and of course 28, which is kind of nice because, right, these chapters can covers voltages and basically how the relationship of, covers electric potential energy, right, the U of E thing. And then in chapter 26, it talks about a lot about voltages. And this one also talk about capacitors and current, right? This chapter we're going to dive even more deeper into how what's going to be on circuit elements, how does a electronic circuit actually work, and we're also going to talk about this thing called resistors that we kind of talked about at the end of chapter 27. Okay, and this is the funnest chapter for me, and because the reason I study physics is because I'm actually interested in electronics. Actually, I was an electrical engineering majors, but when I got to UC Santa Barbara, I got really interested in quantum computing, so that's why I majored in physics to study quantum computing instead of just regular computing, I guess. But that interest, kind of fizzled out towards the end of my undergrad after I had to work like, 16 hours a day pointing a laser at something to to make sure the data actually gets transmitted. And it's just 1 qubit of data. It's really annoying. Anyway, if you're interested in talking about quantum computing, we can also talk to me about it. But this chapter is going to be on non-quantum computing, okay? Where, for example, here you have, I think this is a video card, right? There's these VGA ports here, where, all these little dot stuff on here, what are all these stuff, right? These are like computer chips and stuff, right? We're going to learn a little bit about them, unfortunately, in one class. Well, it's actually one chapter in one class. Right? I can't teach you everything about this. If you're interested in learning all of this stuff, there is the next class, which is all electronics, which is called analog and digital electronics. And anyone who passes class can take it. And it's also an elective for computer science majors. Sorry, I keep talking instead of talking about my stuff versus what we're going to cover. But what's on here are these things are actually these little circles, right? You may have recognized them from when we talked about capacitors last time. So capacitors are these little circles here, right? And the smaller stuff, this thing, is actually a resistor. And all of this, is laid out on this thing called a printed circuit board, PCB. And, taking a picture of it, looks really complicated, right? And it's like, how am I supposed to figure out what the hell's going on here, right? And this is why, okay, when you do, well, either computer science or computer engineering or electrical engineering or physics, I don't know what other discipline also deal with circuits, but I think even like people in psychology has to deal with circuits. But we symbolize these things instead, right? So instead of trying to trying to figure out what's going on here, what we do is we make a simpler version of it, okay? These are called schematics, okay? We're going to make a schematic of a circuit, okay? So therefore, what we're going to do, instead of representing a battery with like, the cylinder thing, we're going to represent a battery with just, this looks a little funky, right? It looks like 2 long bars and 2 short bars, okay? That's what a battery looks like on a schematic, and we're going to play around with them tomorrow in the worksheet. Sometimes, actually, when I'm lazy and most people are, and other people are lazy, instead of two pairs of these things, we actually represent a battery also with just a single short bar and a long bar, okay? And a wire is just a line. A resistor is this squiggly thing instead, okay? And then a light bulb is a circle with a little, I don't know, it's like an octopus-looking thing in there. I don't know what you call it, right? And then if you have wires connected to each other, this is a junction. We talked a little bit about, conservations of current in a junction previously. And it's just lines that has like a little teeth. Just think of it as kind of like a map, right? And then a capacitor, okay, is different from a battery. A capacitor, the two lines are the same length. You try to draw them as close to being the same length as possible. In case you have a switch in your circuit to turn things on and off, just like a light switch, right? You draw it with a little angle line that can be up and down like this, okay? So when the switch is open, it's up. When the switch is down, will look like, let me just draw it. Okay. What I usually do is draw the 2 dots here. So this indicates kind of like the pivot, and this is where the switch actually goes, okay? This is an open switch. This is a closed switch, okay? So let's try to practice doing this, okay? What I'm going to do is I'm going to draw one of them, and then we're going to pick out the other ones, okay? So let's say we have a battery that's connected to a resistor and a capacitor using these wires. It's kind of in the air. What I'm going to do, okay, is I'm going to symbolize the battery with just these double bars like this, okay? Okay, that's in the middle, okay? What I'm going to do is, so I'm trying not to like spatially orient this because these are wires, right? They can be placed anywhere in 3 dimensions. So that's going to mess you up if you try to do that, okay? What I'm going to do is I'm going to take one of the wires, just trace it until I get to something else, okay? So on the plus side of the battery, if I trace this, I get to a resistor, okay? So if I trace this out, I'm going to get to a resistor, okay? And this is how I draw a resistor, okay? I'm going to keep tracing it, okay? If I keep tracing it, it actually branches into 2 points, okay? Right? One of them goes back to the minus side of the battery. So what I'm going to do is I'm going to keep tracing this. I'm going to have it go back to the minus side of the battery, okay? But the other one, it actually goes to the negative side of a capacitor, right? So what I should do is I'm going to trace this until it reaches the negative side of a capacitor, okay? One part of the capacitor, right? Then, right, on the other side of the capacitor, it actually connects to the positive end of the battery, okay? So what I'm going to do is actually I'm going to do this. Capacitor. Okay, I'm going to bring it back over to the positive end of the capacitor, okay? Notice that this drawing is pretty sketchy, let's say, right? So the first try, right? You always end up with something that's, kind of looks funky because you're trying to just follow the traces, okay? What I'm going to do now is I'm going to make it look nicer, okay? The next iteration is going to look a little bit nicer, okay? Because you notice that, right? The idea is that anywhere along this wire, the potential is the same, right? Right? When you have a wire, you're assuming that the potential drop on that wire is going to be 0 because you're kind of neglecting the tiny fraction of resistance that's in these wires. Okay? So one of the things we want to picture is that, I'm gonna switch this resistor until it reaches this side. Does that make sense? I'm gonna take this resistor, I'm gonna just have it move it along here so it looks like this on this side. Okay? Okay. And instead of this wire here, right, kind of being on top, right, I can move this junction all the way to the bottom, right? That's okay. That's the same circuit, right? It's as if I'm just disconnecting this wire from here and plugging it here instead. Since on this wire the potential is the same, I'm plugging it into the same spot. Okay? Right? So therefore, right, this junction, this connection here is actually the same as this one, and this connection here is the same as this one. Okay? So what I'm going to do when I do this, right, to make it look nicer, okay, is to basically still put the battery in the middle, right? But I'm going to have is the capacitor on the left-hand side, right, connected to the bottom. And then the resistor is going to be over here, because I'm just going to squish this over here also to make it look nicer. Okay? Right? And the symbol you want to write for a battery, right, is the squiggly E for the EMF. The symbol for, the variable you want to use for a resistor is R. For capacitor is C. Okay? And if you have multiple resistor, you can label them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever you want. Okay? So, right? So that's how you deal with, converting a actual circuit into what's called a schematic. Any questions about this? This is usually what a lot of students have problem with, getting even in upper division that electronics class. Yeah, Lydia?
Does it matter which side you put the resistor and the capacitor on? Like, does it have to be on the left side?
Sometimes, so maybe. Okay, so be a little careful, right? So when you're tracing this, right, so you're probably comparing it to, I think there's one that does similar things. Yeah, does it matter which side we put it in, okay? So right now what you want to do is what you want to say is, what is this the same? Question mark, right? As if you have a resistor here, the battery here, and a capacitor here, right? Is that the same? Okay. So the way you want to figure it out is that, okay, so usually start with the battery, okay? And if you have multiple batteries, just pick one of them, okay? What you want to do is basically pretend you are a positively charged electron, or known as a positron, and you're just running around this wire, right? So in order to reach the resistor, right, you're going to go right, and you go through the resistor and come back to the battery, right? Is that the same thing if you were to doing this, okay? Instead of making a right turn, you're doing a left turn, but to a positron, you don't care if you're turning left or right, right? So in this case, you are doing the same loop, okay? Similarly, the capacitor, right? You're just going, your little positive charge is just walking along here, hop over a capacitor. It doesn't hop over, but we'll justify that just as a schematic thing, okay? And then you come back to the battery, right? So same thing here. As long as your little positive charge route is doing the same thing, then they are the same circuit, okay? So that's why I didn't want to say yes or no, but maybe, right? Okay. Any other question? Okay. So there are more of these schematics over here can we recognize which of these are actually the same circuit as either this one or this one or this one? They're all representing the same circuit. Okay, and there's actually more than one. Okay. Okay. Oh, you want to find the one that is not represented by this circuit. Okay, so you want to check out the ones that are. Okay. See if we can figure that out. Yeah, there's one that is not. That's good. Okay. How many you think is A that is not the same as these guys? How many think is B? How many think is C? Good. Okay. So then D is D. I'm going to tell you is the same. Okay. It's just drawing in a triangle. Typically, you don't want to draw it at these crazy angle because it looks kind of funky. Drawing it on a grid will make it simpler to analyze in the future. But this one is not. The reason is that in order for the battery, so pretend you're a little positive charge and you're walking, right? The only way you can get to the capacitor is to go through a resistor, right? This is not allowed because the original circuit states that, well, you're not going through the resistor first before you meet the capacitor, right? This is the why this circuit is actually different. Okay? All right, good. Now, let's do a little bit more. Now with that, with kind of like how to draw a schematic, what we're going to do is introduce you to two different laws that will, well, we actually got introduced to them a couple of chapters ago. We're going to apply these in order for us to do circuit analysis, okay? So the first one is Kirchhoff's junction law, where whatever amount of current that flows into a junction, the same amount has to flow out, okay? So the analogy I like to use for this is that if you have a river, right, that flows in, let's say you have two rivers that flows into some sort of lake, right? And you have three rivers that flows out of the lake, right? We call this I1, I2, I3, I4, I5, right? We declare that these are going in, these are going out, right? In order for you to keep the lake level the same, the amount of current, amount of water flowing in has to equal to the amount of water flowing out, okay? And that's how I want you guys to memorize this, okay? Okay? Because me giving you this equation is not going to help you on the test, really, right? Because you have to kind of have the conceptual understanding of it, okay? Amount of current flowing in has to be amount of current flowing out, okay? The second one is usually the more difficult one. We kind of talked about this when we talked about electric potential energy, okay? Where if you go around a loop, okay, meaning you start off here and you go all the way around and come back to the same point. If you go around the loop, the change in potential around that loop is 0. Okay? Okay? And the picture you want to do is, let's say you're going on a hike. If you're not a big hiker, just pretend you are, right? Let's say you park your car right here and you start your hike up the hill and you go down a valley and you come back up. So you're doing a loop, right? A hike that goes around a loop, right? Right? In order for you to get back to that same point, right, your elevation is the same, right? Right? Your beginning elevation and the ending elevation is the same, right? You end up at the same height. Okay? Therefore, the amount of gravitational potential energy you have is the same. The same idea occurs with circuits where instead of gravitational potential energy, you're dealing with electrical potential energy. Right? And electrical potential energy can be quantified by just multiplying by the charge with the potential, right, or the voltage. Okay? So if you start off here, and let's say, okay, so let me just do an example of how you deal with this. Right? You can pick any point on your circuit to start. The book picked this point, but we'll see that the equation actually doesn't change. Okay? We start off here, right, and we're going, what is this, clockwise, right? The first thing we're going to see is we're going to have some potential change due to this device here. It's probably a resistor, but it doesn't have to be, right? Therefore, this will give you a change in potential of delta V1, okay, right? Whatever it is most, this is actually a battery probably if it's positive, okay? But you keep going on this loop until you run into your second device, right? And then there you get another change in potential, delta V2, right? And then you get to the third component, delta V3, right? And then you follow this little path once again, delta V4, okay? Because this is the total change in potential around a loop, that always have to be equal to 0, right? You end up with the same potential, okay? Another way to think about this, okay, if it's this way works, okay, you don't have to do both, you just have to do it one way. The second way to do this is say, okay, what I'm going to say is that the potential here is 0. You can pick any point on your circuit to be potential equal to 0 if it's not grounded already, okay? Okay, if I pick this point to be 0, right, if I go over here, I'm going to get plus delta V, right? Then if I go over here, I get another delta V2. I go get delta V3. I get delta V4, right? I keep gaining this potential. And this delta V can be negative, right? Be careful, right? But I end up at the same point. I know the potential there is 0, right? Because that's not what I defined it as. Notice that we end up with the same equation, right? Either way, okay? And this is how you kind of mathematicize these circuits, okay? You take your circuit and you just have, if you want to do calculations on it, right, you have to write some sort of equations, right? Right, so this is one law that will give you the equation. The other one is going to be, right, the amount of current going in, the amount of current going out has to be the same into a junction. Okay. So, and let's go through this tactics box. Usually I don't, I just kind of blazes through them. But I really like the way that the book describes it, okay? So the first thing you want to do is draw the circuit diagram. So always, this is, you know, where we have always the what's it called? The setup part of your problem, okay? One thing to note, we're going to see this. So once you're, let's draw this diagram, right? The one we had before with one battery and one resistor, okay? Okay. Right, so this is drawing the schematic of the circuit diagram. The thing you want to do is also assign, that means you get to decide which direction the current is in. I think from the last worksheet, was it, or is it 2 worksheets ago, where some of you guys are asking, oh, which direction is I5 going in, right? You actually get to decide, okay? But sometimes what happens is that if the answer turns out to be negative, that means instead it's a negative. So let's say if you have a current flowing out this way, right? Let's draw this, right? Let's say you have some device, I don't care what it is, to another device, right? This is I5, okay? If you declare the current this way, and this turns out to be negative 9 amps or something like that, that means in reality, it's actually a current going the other way, right? Right? For this class, I actually don't care if you end up with negative numbers, but I know some professors, they say that the current value should always be positive, and you have to assign the direction correctly, okay? So if you end up with a problem where you end up with a negative current, all you have to do is just say, well, I assigned the current in the opposite direction. I'm just going to assign it back the other way and change the sign to positive, okay? Right? So a negative 9 amp going this way is the same thing as positive 9 amp going the other way, okay? Let's see, okay? So, and as you travel around the loop, okay, whenever we run into a battery, okay, a battery, what it does is it gives you potential, right? It gives the little charge more energy every time it goes through it, right? So when you travel from the negative side to the positive side of a battery, you will gain whatever the EMF of that battery is, whatever voltage that battery happens to be, okay? Okay. If you're going in the opposite direction, let's say you're going from the positive end to the negative end, right? It's as if you're falling down, okay? In that case, right, you actually lose EMF amount of potential. Okay. Okay. Resistors are either simpler or more complicated depending on how complex the circuit gets, right? When you're going across a resistor, if you're following the direction of the current, you always lose potential. Okay? What I want you guys to picture is that resistors are kind of like little cobblestones in a river, little rocks and reeds and stuff like that, right? If the water is flowing, at a certain speed, once it reaches this resistive stuff, right, it's going to slow down, right? So therefore, you're always going to lose energy when you have to go through something that's resistive, okay, if you are following the direction of the current, okay? Okay, so the current is this way, right? So make sure that it's always negative the current times the resistance, okay? Because that's Ohm's law, but then this extra negative sign is because we're doing circuit analysis, and we know that whenever we go through resistive stuff, we're going to lose potential, okay? All right. And then, of course, apply Kirchhoff's loop law. So let's do an example, okay? Let's start with the simplest one possible, okay? Where we have one battery, one resistor, okay? Sometimes the resistor is called load because actually what's going to happen is that you're going to drain power from the battery from this, okay? So this battery has a EMF of 5 volts, and the resistor is 250 ohms, okay? So what I'm going to do is I'm going to start off by drawing the circuit diagram, right? Instead of drawing this, I'm going to draw a battery, which is these two sets of parallel lines, okay? And then I'm going to start off up here. I'm going to pretend I'm a positive charge. I'm going to follow this until I see a resistor, right? And I draw the resistor, okay? And then I come out on the other side of the resistor, follow it until I get to the negative end of the battery, okay? Follow this procedure all the time. I know for this circuit it's kind of silly, but this procedure works, okay? You have to follow the lines, okay? Okay. And since this is a battery, I'm just going to declare that that has some EMF. And since this is a resistor, I'm going to call it R, okay? What I'm going to do is I'm going to pick the direction of the current, okay? You would think that, well, normally you would think that, well, the direction is going to be, since this is positive, the current's going to flow this way. And you would be right. I'm going to do the wrong thing. Well, I don't think it's wrong. I'm going to do the opposite thing. I'm going to say that, well, I don't like my current going that way. I'm going to assume that the current goes this way and see what happens, okay? Okay. And I'm going to do is I'm going to travel along the loop as if I'm a positive charge, okay? And I can pick any point I want to start to travel, okay? Let's say I'm going to pick this point, okay? Right? If I pick that point, I'm going to start off here. I'm going to go in the opposite direction of a battery, right? I'm going from the positive to the negative side, right? So I'm going to lose EMF of potential energy, okay? So what I'm doing is I'm going to be applying Kirchhoff's loop law, delta V over a loop, right? Okay? So I'm going to lose EMF amount of energy by going backward here, okay? I'm going to go along here, okay? And then I'm going to reach a resistor, okay? The current is still going this way, so I'm going to go over this resistor, okay? And that's going to be minus the current times the resistance, okay? So whenever you go over a resistor, you get current times the resistance worth of potential drop, okay? And now I end up at the same spot. Since I'm at the same spot, I completed the loop. If I complete the loop, the potential change there should be 0, okay? Okay. Right? And that's applying Kirchhoff's loop law, okay? What I'm going to do is, well, if I want to solve for the current, right, because we know the EMF, we know the resistance, we want to solve for the current. I solve this equation for the current. It's going to be negative I times R. Let's just do it the long form since it's the first time. Right, divide both sides by R. So I is actually negative EMF over R. Right, the EMF is 5 volts. And then R is 250. So that's actually 1 over 50. So that's 0.02. Okay? And a voltage divided by a resistance should give you the SI units for current. What's the SI units for current? Amps. Okay? Notice that my current is negative. Okay? In this class, I don't care if you have negative as the current in your answer. Okay? In other classes, or you go on to do electrical engineering, and you say, oh, Dr. Tu told me it was fine for me to leave that as negative side. Don't say that, okay? Your boss may yell at you, okay? Or he'll come and yell at me, okay? Right? So what you want to do, since I have a negative current, what I'm going to do is I'm going to do my corrective thing, okay? So that means, oh, I've declared the current the wrong direction, okay? What I'm going to do is I'm going to redraw the diagram, okay? Or you can just erase the old one, right? Instead of making the current go down, I'm just going to declare the current goes up, right? And that current is going to be positive 0.02 amp. Does that make sense? Okay. Right. Right. All right. All right. You guys want to do a more complicated one? Okay. You guys have a piece of paper out? Let's just try to do this together. Okay. Just follow along. Okay. So the you know this whatever website I got this from already gave me the circuit diagram, so I don't have to do that translation, right? What I want to figure out is how much current will flow through this circuit. Okay? How do I do that? Okay? So the EMF 1 is given to you, EMF 2 is given to you, resistor 1 is given to you, resistor 2 is given to you, but we don't know what the current is. Okay? What's the first thing I should do after I draw the schematic? Should I do, remember, what's the first thing I should do? You have to pick the direction of the current, okay? So typically, if you want to end up with a positive current, and it's going to work like maybe 80% of the time, is you take your biggest battery, in this case, which is EMF 2, okay? You pick your biggest battery, and you just have it push. This is the most dominant current producing source, okay? So what I'm going to do is I'm going to say that, well, since this is the biggest battery, I'm going to declare that the current goes this way, okay? On this circuit, there's only one current, so I don't need to label it 1, 2, and 3. In the future circuit we're going to deal with, we're going to have multiples, okay? What it's going to see is that the reason we only have one current is that all along the circuit, right, we're only on one path, okay? We don't have a split in the path at all, right? So we don't have to label it 1, 2, and 3. What should I do next? Now that I've defined the current. Anyone on this side of the room? Alex, Kayla, Caitlin? I'm sorry? Declare your 0 point or apply Kirchhoff's loop law. Either way works, okay? So the previous one, I did Kirchhoff's loop law with where, I just did the equation. Okay, what I'm going to do is I'm going to declare one of these points at 0. Okay, I'm going to say that V equals to 0 here. Okay, right. I'm going to do is follow the loop along the direction of the current. Don't go backward. Okay, so if I declare this to be 0, if I go over this battery, okay, and this battery is drawn with a single, instead of the two parallel ones, it has the single version of it. So this is equivalent to same thing as this, okay? So don't get confused by that. If I can draw that correctly, that'll make it easier, right? It's the same, okay? So I'm going to gain EMF2 amount of potential, right? So I'm going to go from 0 to plus EMF2, okay? And now I'm at this point. I'm going to keep following along. When I reach this R2, since the current, right, is in this direction, right? It's the same current, okay? What I'm going to see is that while I'm going across a resistor along the direction of the current, this is where the water is flowing through the reeds and the cobblestones and stuff like that, right? The current's going to slow down, okay? So I'm going to lose whatever the amount of current is times the resistance of that cobblestone resistor thing, okay? Next, I keep following this along. Now, right, I see a battery, okay? Which should I be gaining or losing EMF 1 in this case? 1 here. I'm sorry? Losing, right? Why are we losing it? I thought batteries are good. Right, we're going backward against the battery. Exactly. So we're actually losing EMF 1 amount of potential. Now we're on this side, okay, and we get to R1. Since the current is still going this direction, right? The current, right, is going across this resistor. We're going to lose I times R1 amount of potential, okay? And now we end up at the same point. We end up with 0, okay? So therefore, now we have our equation to solve, okay? This is where the math comes in, okay? We know E2, we know E1, we know R1 and R2. The only unknown is the current, so I can solve this equation for the current. So therefore, what I can do is to do my little algebra steps. I personally like to move all the negative stuff to the other side, therefore it changes to positive. Then deal with the rest of the equation. So E2 minus E1 equals to I1 R2 plus I1 R1. Was that okay with everyone? Okay. Now I can factor out I1, right? And then divide both sides by R1, R2. Okay. And therefore the current is actually EMF2 minus EMF1, R1 plus R2. And hopefully I end up with a positive number, but if I end up with a negative number, it's okay, right? I just need to switch the direction of the current afterward. Okay, so EMF2 is 9 minus 5. Resistor 1 plus resistor 2 is actually 400 ohms total, 150 plus 250. This is in volts, this is in ohms, okay? And since I know these are all SI units, the units will work out to give me amps at the end. So this will be 4 divided by 400 amp. In other words, it's going to be 0.01 amp. Another way to write that is 10 milliamp. Okay? Remember, milli is 10 to the minus 3. Okay? Okay? So the answer is actually C here. All right. Okay? All right. There's a couple of examples in the textbook. I don't do them because the best way to learn how to do circuit analysis is just try to do the example yourself, make a mistake, okay, which is okay, get the answer wrong, which is fine, and then go back and look at the examples and see what the book did and change what the book did from where it's different and fix it from that point. Cool?
So was the starting point, is it arbitrary?
Yes, you can pick wherever you want. So we're gonna in the later section in this chapter, we're gonna have this thing called ground, and that's just the book picking where the starting point for you. But you can, in general, just pick any starting point you want. Okay. Okay. So if you want to go to this example, right? Instead of starting here, start here, and see if you end up with the same answer. Okay. All right. Got about 4 more minutes. Yeah, we can talk about this in about 4 or 5 minutes. Okay. So the next I'm going to talk about is that, remember the first thing when I introduced this thing called resistor, they also call it a load. Okay, remember this was like this, right? This was the EMF, this has some R. Sometimes this is called a load. That's because when current goes through a resistor, it actually heats up the resistor. It dissipates energy. It converts electrical energy into thermal energy. Okay? And going back, I don't know what that A is there. So since we're dissipating energy per time, right, this goes back to our general physics 1. This is actually called power, right? Power is how much energy you are either gaining or losing per unit time, okay? In our case, since we're doing electrical energy, okay, the amount of change in potential energy over the change in time, okay? Electrical potential energy is just the charge times the voltage, right? In this case, right, the voltage across this resistor, right, since this is EMF, the voltage across this thing is also EMF, okay? The amount of voltage across the resistor is actually just the EMF. Sorry, I probably did put the delta, okay? So therefore, okay, if you take the time derivative of this, right, on this side, and you take the time derivative for every part of this, okay, I'm going to copy down this here, right? Time derivative of energy is power, okay? And then the time derivative of charge is what? Anyone? What is charge changing per time? That sounds like current. Great. You guys got great intuition about this, okay? So power is actually current times the EMF that you are supplying, okay? Okay. So that's coming out of the battery, okay? That's the amount of power coming out of a battery. If you have, but on the other side, we have a resistor, right? In that case, what's happening is that the same concept applies, but now we kind of have to kind of think about the microscopic electrons that's moving through these resistors, okay? As these electrons are actually going backward, right, through here, what's happening is that there's going to be a change in thermal energy. This TH here is thermal energy. I know we don't talk too much about thermal energy, but it's just think about it as energy that's of heat. Okay, something's hot, it has higher thermal energy. Okay, that change in thermal energy is also similarly, right, similar to this, right, is the charge, whatever value that charge is, times the change in potential across that resistor, where this is, you know, the change in potential. Okay, right, if you're mapping the voltage map instead, okay, instead of distance. Okay, so power through the resistor, okay, is once again basically just the delta E over delta T, right? That turns it into a derivative, okay? And therefore, right, this derivative also hits this the charge, right? And once again, you guys figured out that, oh, this is just current, okay? Therefore, right, the power that is dissipated by resistors is just the current going through that resistor times the potential drop across this resistor, okay? So notice this is a positive number, okay? Okay. All right. We won't do the quick check, but I'll just derive a couple of more equations. So we have this equation here, but we also have Ohm's law. So this is Ohm's law, right? Change in potential across a resistor is just the current through the times the resistance, right? That's what we derived last week and what we've been using when we deal with circuits with resistors. What I can do is then take this, right, and plug it in here. If I do that, right, I end up with I squared R, okay? If I solve this equation for I instead, I is equal to delta VR over R, right? And I do a substitution in here instead, then I end up with V squared over R, okay? So this is, you know, just 1, 2, 3 different ways to write the same equation, right? Okay? So if you were given current and resistance, you should use this one. If you were given voltage and resistance, you should use this one, right? If you're given current and voltage, you should use this one. It's whichever one is easiest, right? Combining these two laws together, right, allows you to solve for power for anything that has to do with resistors and current going through it, okay? All right. So I'm out of time. So wrap up. And any questions?